Good morning, everybody. We are going to discuss about RRK theory, which stands for Rice-Armsburg-Castle treatment. It's a type of unimolecular. It's a type of theory for unimolecular gaseous reactions, and we already have seen the last videos that we are theory for unimolecular reactions like Interbank theory and Hinchelwood theory, and these two theories we have discussed in the previous classes, and now we are going to discuss about the RRK theory. With a slight modification of Lindemann-Christian mechanism, the theory for unimolecular reactions can be written, and following the Hinchelwood suggestion can be written as following. And in this way, M is any molecule, including another A, that can transfer energy to M when a collision occurs. A star is the energized molecule, and A double decker or A ash is the activated molecule. To become an activated molecule, the molecule A must acquire at least energy, and this energy is known as is written as here epsilon 0 star. Okay, then these are the terms: A star, energized molecule; A double dash, double decker or A dash is activated molecule. Epsilon 0 star is the critical energy or the lowest energy required for the activation. Then we are going to its derivation part. In the subsequent theoretical treatment, the rate constant K2 was not treated as a constant, but was considered to be larger the greater the value of epsilon 0. And we can be written as in the general form as follows. That is K dash is equal to K2 into K1 upon K minus 1 by all upon 1 plus K2 upon K minus 1 into concentration of M. In the Hinchelwood version, both K2 and K1 upon K minus 1 are treated as independent of epsilon star, that is the amount of energy in the energizer molecule. And we know that Hinchelwood's result involves a critical energy epsilon 0 star. It is a critical energy, that is a minimum energy you get to activate the molecule, and rather than epsilon 0. After the derivation of Hinchelwood formula, which is derived in 1927, three scientists, there are OK Rice and H.C. Ramsberger, and independently L.S. Castle. They proposed the theories in 1928, just in the gap of 1 year. One in both K2 and K1 by K1 minus K1 by K minus 1 were treated as dependent on epsilon star. These theories are referred to as jointly the RRK theory. That is proposed by Rice, Ramsberger, and Kessler. In this theory, K2 is replaced by K2 epsilon star and K1 by K minus 1 by F of epsilon star, and which is distribution function F of epsilon star is a distribution function, and this equation can be written as dk1. That is dk1 is a which represents the small change in energy, that is epsilon 0, and epsilon 0 is changes to epsilon 0 plus d epsilon 0 star. Then to get K dash, we integrate the terms between the minimum amount of energy epsilon 0 and maximum amount of energy infinity, and can be written as the follows: K dash is equal to integral epsilon 0 star to infinity in K2 f of epsilon 0 all upon 1 plus K2 by K minus 1 into concentration of M and dE star. Since the molecules are loosely bounded, the energy can be easily distributed among different modes of vibrations. And this can be explained just by a molecule C2H6 star. This ethane can pass into normal modes of vibrations. As a result, what will happen? There will be extension, or the vibration of the CC bond will break if the energy is sufficiently large, and we get this CH3 star medial free radical. C2H6 upon gives 2 medial radical, CH3 radicals. Okay. Then the K2, which depends on the energy E star, and integrate to get to K2, we'll take the help of statistical thermodynamics. For that, we consider that our system is divided into S degrees, vibrational modes of freedom. And this contains J count of energies. That is written here. Okay. The K2 which depends upon the energy epsilon star. And in order to get K2, we will take the help of statistical thermodynamics. For that, we consider that our system is divided into S degrees of vibrational freedom. And this S contains J count of energies. Okay. In other words, we can say that we are having J amount of objects. And just imagine that we have J amount of objects. And these objects that has to be distributed among S number of boxes. That we have just J amount of objects and this which has to be distributed in S number of boxes, each of which may contain any number of objects. So there is no restriction in filling the objects. Okay, J count of numbers objects which is to be distributed in S number of boxes and S number of boxes, and each of which may contain any number of objects. So there is no restriction in filling the objects. Then the thermodynamic probability for such a situation, as we have already seen in previous classes, that is W can be written as follows. Just like this, W is equal to J plus S minus 1 all factorial by J factorial into S minus 1 factorial. As we have already discussed in the UG classes. And now let's consider that out of J count, we already assumed that we have J count of numbers, J count. And out of J count, one particular molecule has M count. That has to be subtracted from this J equation. So the equation is converted into J minus 1 plus S minus 1 all factorial by J minus M factorial into S minus 1 factorial. Okay, then the probability that a particular oscillator has M conda and all S oscillators have J conda is given by the ratio as follows. R is equal to W by W W dash by W is equal to J minus M plus S minus 1 all factorial into J factorial upon J minus M factorial into J plus S minus 1 factorial. Now further what we can do is apply Stirling approximation with this particular expression. And suppose we have the Stirling approximation as n factorial is equal to n raised to n by e raised to n. This is a Stirling equation. Now the distribution factor f of epsilon star that we seen in Hinchelwood theory, which is in this form, that is f is equal to final result f is equal to 1 by s minus 1 factorial into e by rt all raised to s minus 1 into 1 by rt into e raised to minus e by rt dE. And by applying this equation from Hinchelwood theory into our equation, we get that k dash is equal to okay, k dash is equal to integral epsilon 0 star to infinity k double tick into e star minus e 0 star by epsilon star into 1 by s minus 1 factorial into e star by kt all raised to s minus 1 into 1 by kt into e raised to minus epsilon star by rt dE star by 1 plus k double tick by k minus 1 into concentration of m k minus concentration of m into e star minus e 0 star by e star all raised to s minus 1. can give this equation as equation number 1. And now the equation can be reduced by following substitution that we written here, that is x is equal to epsilon star minus epsilon 0 star by kt, and b is equal to epsilon 0 star by kt, and d star by kt is replaced by dx. It's for reduction of this equation. And limits of integration, the limits of integration can be changed to 0 to infinity. Instead of epsilon 0 star to infinity, we can change this to 0s to infinity. And now our equation is reduced as follows. That is the k dash, and this equation k dash is equal to integral 0 to infinity k double tick x raised to s minus 1 into 1 by s minus 1 factorial into e raised to minus x plus b dx by 1 plus k double tick by minus 1 into concentration of m. This is the concentration of m into x by x plus b all raised to s minus 1. And now we are going to solve this integration. We can written as k double tick or k h into e raised to minus b by s minus 1 factorial as the constant terms, and the other integral terms, that is integrate from 0 to infinity x raised to s minus 1 into e raised to minus x dx by 1 plus into 1 plus k double tick by k minus 1 into concentration of m into x by x plus b all raised to s minus 1. And this can be written as follows, just like this. Also written as just like this. And when the concentration of m is very large, that is a high pressure first order limit, this expression reduces approximately into, that is our this expression, it's a big expression which is reduced into k infinity dash is equal to k dash into e raised to minus epsilon 0 star by kt by this assumption. And it's a simplest equation, just like this. It's already solved equations. Then and over here with experimental arguments, we can see that the value of s is to be taken as half the number of modes of vibration, that is s, therefore s is equal to 1 by 2, and therefore the experimental and theoretical values are unrequited. That is in this equation. We assume that the experimental arguments, we can see that the value of s is to be taken as half the number of modes of vibration. Therefore, s is equal to 1 by 2. Okay. Then, therefore, the experimental and theoretical values are required when we take the s as 1 by 2. Now, moving to limitation of RRK theory. Even though RRK theory has rectified the limitations of Lindemann theory and Hinchelwood theory, still it contains limitations. And it can be written as first one, it is impossible to predict the value of s. Of course, we know that it's impossible to predict the value of s is the number of degrees of freedom, vibrational freedom. And using RRK theory, the next limitation is using RRK theory, we cannot we're not getting the satisfactory value of the pre-exponential factor a. And moving to next limitation, the significance of k dash is not also rather unsatisfactory. So there is another theory called RRKM, which is modified from the RRK theory. That is just written here, that RRKM theory, which rectify these limitations of the RRK theory, but it's not in our syllabus and we do not need to study this one. Okay, thank you. It's all about my topic RRK theory, and thank you all. And here I attach the notes for RRK theory. It's referred from Puri Sharma Patania for Principles of Physical Chemistry.